Hey guys, we're going to look at 3.1 today, at least part of it. It's going to talk about functions and function notation and evaluating functions and things like that. So a little bit about domain and range. And I really didn't think that the notes went very well with the homework. So what I ended up doing was actually just taking a bunch of examples out of the book and using those as examples for the notes here. So we're actually not going to use the what's typed out here very much at all. So if you write anything down, you might want to do it on the blank side of the pages, as part of your notes for if you want to write this stuff down. So, but I've referenced each. So just defining a relation, which this stuff is definitely stuff you've talked about before. So relation is any set of word pairs. A function is a special type of relation where each input has exactly one output. So every time we plug a number in, we get the same answer back out. And so when we talk about inputs and outputs, another way of talking about inputs is that it's the independent variable. And we've been talking about that recently, that that's also x, our independent variable. And our values that make up the inputs, the independent variables, the x's, make up our domain. And then the output, or the dependent variable, in this case, generally y, makes up the range. So we take all of our collection of inputs, and that would make up our domain, all our collection of outputs, that would make up our range. So a lot of times we think of functions as machines, that as long as they are working correctly, they are functioning. What that would kind of imply that every time I put something in, I should get the same thing back out. Or not the same thing back out, but I should always get a consistent thing back out. And so if you think of a function like a soda can machine, there can be, the input would be the button that you press in order to get a certain can of soda out. And so you hit the Pepsi button and the Pepsi can comes out, and you hit the Coke button and the Coke can comes out, and you hit the Sprite button and the Sprite can comes out. So as long as that's working properly, we're good to go. Okay, and sometimes it's okay if if there's two Pepsi buttons, and then you hit, it doesn't matter which one you hit, they both spit out the same output, right? The two different inputs can have the same output. That's okay. Where things go wrong is if when you hit the Pepsi button, one time a Pepsi comes out, and another time a Coke comes out, right? You wouldn't be very happy. And so if one input could give you two different outputs, that would be something that's not functioning. So that's where I'm going to move to this next idea. So it wasn't too weird, but of course, let me know if you guys have questions, and yeah, I'll be around. Right. Problem like where it is in the book. So if you're wanting to see it, looking at page 161, thought this was a pretty interesting example of a function in kind of real life, like in a way, in not really mathy terms. Okay, and so what they're looking at here is a coffee shop menu, and just real simple menu, just an item and then a price of that item. Okay, so they're asking, is price a function of the item? So if I think of the item as being my input, is the price a function of that? Right. So if I say, hey, I want a plain donut, they would tell me that costs $1.49. Hey, I want a jelly donut. Okay, that costs $1.99. Hey, I want a chocolate donut. Hey, that costs $1.99. So every time I pick a particular input, it corresponds to a particular output. So, I don't say I want a plain donut, and then one time they say it's $1.49, and then another time they say it's 89 cents. Right? There's only one output associated with each input. Okay? So yes, the price is a function of the item. Well, does it work the other way around? Is the item a function of the price? Okay? So is the item a function of the price? So if I input the price, do I always get the same item back out? And so what they've done here with that is, since two of the prices were the same, right, we wouldn't have to list it twice. And so if we say, hey, I want something that costs $1.49, they would just give us a plain donut. But if I said, hey, I want something that costs $1.99, well, one time they could give us a jelly donut, and the next time they could give us a chocolate donut. So this particular input has two outputs. And so what that means is that the item is not a function of the price, because one input could give us multiple outputs, and that's not okay. So just kind of interesting way to think about that. That's not necessarily math related. So hopefully, and so I wanted to shift that into think about it in something that's a little bit more mathematical. And so here they're just giving us a table, and they don't really tell us what this table is about, but they say that this part up here isn't really too much difference from what we're talking about here, but the inputs are n, and then the outputs are q. So this would be kind of like our x's, and these would be kind of like our y's, right? So as I plug these numbers in, right, these are the answers that come back out. And so is q a function of n? Okay. So for every input, do I only get one output? So when I plug in 1, I get 8, yes. When I plug in 2, I get 6. When I plug in 3, I get 7. When I plug in 4, I get 6. When I plug in 5, I get 8. Okay? So every time I plug in 1, the only answer I get is 8. Right? Every time I plug in 3, the only answer I get is 7. Every time I plug in 2, the only answer I get is 6. So yes, q is a function of n, because each input has only one output. Okay? Now what about this table down here? Right, this one shows the ages in children, that would be our input, versus the height of this child, okay, and that would be the output. So they've measured a bunch of different children, and so they had a child that was age 5, they were 40 inches tall. They had a child that was age 5, that was 42 inches tall. A child that was age 6, 44 inches tall, so on and so forth. And so is the height a function of age, right? So for every input, is there only one output? And so this is actually not a function, because these two inputs have different, right, same input, but different outputs. And that's not okay. So in this case, height is not a function of age. Okay? So again, kind of seeing it a little bit more mathematical, but still kind of relating it back to the idea that each input can only have one output. So because we plugged in 5 twice, we've got 2 different answers. That's not a function. Okay? Then I want to go back and talk about domain and range again. So remember we talked about domain being the set of all the inputs, all the independent variables, all the x's. Okay. When we're looking at domain in something like this, where it's something that's discrete, where it's just individual points, okay, what we do is we write it in what are called curly braces, which is something that has to do with sets. In math, we use curly braces. That is not a great curly brace. And all we do is, when we're talking about domain, we're listing the inputs, okay, listing the x values, or in this case, n values, listing the independent variables. So there are a couple rules. We always go from least to greatest, and then we never write down the same number twice. So if I'm looking up at there at table 4, the domain would be 1, 2, 3, 4, 5. That'd be the list of all the inputs. Okay. The range would be the list of all the outputs, all the y's, all the dependent variables. It follows the same rules. We always list them from least to greatest, and we don't repeat a number twice. Okay, so if I was going to list the range for table 4, I can see the smallest number there is 6, but there's 2 of them, but I'm going to write it once. The next number is 7, and then there's 2 8s. Again, I'm only going to write that once. And so that'd be the range for that particular relation. So we don't repeat numbers, and we go from least to greatest. And we use curly braces around when we're writing discrete domains and ranges. And we'll talk about ones that are continuous later in a different section. So if I was going to write the domain and range of table 5 here, so I want to do for the domain, I want to look at the inputs, so the set of all the inputs. So notice that there's 2 5s, so I'm only going to write that once, and everything else is unique. So the domain here would be 5, 6, 7, 8, 9, 10. And then the outputs, looks like they're all unique, and they are all going in order, so I'm just going to write those down the way they are. So 40, 42, 44, 47, 50, 52, and 54. So again, what I'm talking about here is all the inputs there are, all the outputs there are. What are the numbers I can plug in? What are the answers that would come out? And what are the numbers or values I could plug in? What are the values that could come out? They're not connected at all. Like 1 hasn't anything to do with 6, right? 2 doesn't have anything to do with 7. It's not like that. It's just purely a list of numbers. So that's all it is. So that's how you find domain range. So, we can use tables also to evaluate functions. So if we knew that, kind of look at what they're saying here, that g of 3, right? And this is saying g of n, so that g is a function of n. So n must be my input, and then g would be my output, whatever g and n stand for. Okay, so n is the input, g is the output. So they're saying, let's make the input 3, right? What's the output when the input is 3? So here's my inputs, and the output associated with that is 7. So using a table to evaluate a function, so g of 3 is 7. I can also do it the other way around, so it says g of n is 6. So notice that, it's not saying that n is 6, it's saying g of n is 6. So this is saying the output is 6. What's the input? What input would give me an output of 6 as a way, another way of saying this? Right, so see how much shorter that is, right? G of n equals 6. This is asking what input gives an output of 6. What input gives an output of 6? So look here, there are multiple outputs of 6. So there are multiple inputs that give us that output. So n could equal 2 or 4. I believe when you're doing the homework, it asks for like a comma separated list. And so it would look like that, 2, 4. So there's using a table to find values. Next, we're going to look at using a graph to find values. So again, reading this, evaluate f of 2. So here's our function f of x. All right, so the y values being the function of x. Okay, so what x's I plug in to get certain y values back out. So it's saying plug 2 in for x, right? That's one way to think about it. Or if 2 is the input, what is the output? Or probably best here, if 2 is the x coordinate, what is the y coordinate? Okay, so I'll go to where x is 2, and I go to where I hit the graph, and see what the coordinates at that point are. So that'd be 2, 1. So f of 2 is 1, because 2, 1 is a point on the graph. Okay. So if they give you an x value, they're asking for a y value. So go to where that x value is, find the graph, and then see what the y value of the point is there. So like if I said, hey, what's f of 0, right? So f of 0. So here's where x is 0. Oh, it's also 1, right? So f of 0 also equals 1. And if I said, what's f of 1? Okay, well, here's where x is 1. That the y coordinate there is 0. Okay. So here's the other way around, right? So now they're giving us the y value. They're saying what x values have a y value of 4, right? So basically, what's this if the y is 4? And so we go to where y is 4. And I want you to notice that we could go to the left and hit that graph. So there's a point there. I could hit negative 1, 4. Or we could go to the right and also hit the graph. And so it could be 3, 4. So there are multiple inputs that give us the same output. Okay? So again, I think what they want here is that x equals, and a comma separated list is what they're going to look for. So x could be 1 or x could be 3 and have the same output. Okay, so using a graph, again, here they're giving you x, it means they're asking for y. Here they're not giving you x, right? So that means they're giving you y, and so that means they're asking you for x. Okay, I think these notation here is work pretty well, right? If x is 2, what's the y value? If y is 4, what's the x value? All right. Of course, we can evaluate a function given that function and a value to plug in. Pretty basic, right? So g of m equals the square root of m minus 4. Evaluate g of 5. So g of 5 equals the square root of 5 minus 4. Of course, square root of 1, which is 1. So g of 5 equals 1. If I was going to plot that point, it would be 5, 1. And if I was asked to do it again, like, I don't know, 7 or 12, I don't know, whatever, it doesn't matter. So let's say g of 12, right? So that'd be square root of 12 minus 4, which of course is the square root of 8, which doesn't have a nice square root, but if we did reduce it, simplify it, would be 2 square roots of 2. So, but if you're trying to plot that point, you would plug that into a calculator and see what that is. You'd say like 12. I think the square root of 2 is like 1.4-ish. So 2 times that would be about 2.8-ish. So we'd be plotting a point about there, if you're trying to graph it. So, but just plug the number in and do the math out. It's pretty easy. You guys have definitely done that before. So the other way around, right? So what if they're not giving me the input value they're asking for? Here's the output value. What's the input or inputs that give us this output, right? So essentially, notice it says solve here. We're solving for this. We want to figure out what P is. And so I'm going to take that 3 and I'm going to replace this with it. So take that 3 and it's going to replace that. Okay, it's not going to get plugged in for P. It's going to replace that whole side. So I'd say 3 equals P squared plus P. Oops, 2P. Okay, well, if I want to solve for P here, because this is quadratic, that means I need to factor this. And so in order to factor it, I need to get one side to be 0. So the first thing I need to do is subtract 3 to the other side. We did this pretty recently. So 0 equals P squared plus 2P minus 3. It's going to be some easy AC factoring. So I want AC, A times C is negative 3. Need those to add to 2. So factors of negative 3 that add to 2 would be negative 1 and 3. Because this is easy AC, I can just go straight to my factors. P minus 1 and P plus 3. Those equal 0. And so what's P equal to? Well, P would have to be equal to positive 1, and P would have to be equal to negative 3. Okay. So again, what that means is that if I plugged in 1, I would get 3 as my answer, but if I also plugged in negative 3, I would also get 3 as my answer. All right, so those two different inputs can have the same output. That's fine. So don't forget about factoring when you're dealing with quadratics. You just solve a quadratic. All right, last is the homework. So I've changed this example a little bit just to make it a little bit more like the homework for you guys. But we have a function that we're evaluating at different values, and so it's kind of some expressions. And we've got this thing over here that's I added on, again, just try to help you make it more like the homework. So they just want us to plug these things in here, and this one's going to be, I'll show you what that means. But so I'm just starting off with the first one. I want to find f of negative 5. So that'd just be negative 5 squared plus 3 times negative 5 minus 4. So we should be following PEMDAS here as we're simplifying this. So I'm looking at exponents first, which of course would be, negative 5 times negative 5 is not negative 25, it's positive 25. So I'm going to do this really thoroughly. I would write it out again. And then I want to do any multiplication. So I'd have 25 plus, which would be negative 15 minus 4. And then we would do any addition subtraction from left to right. So 25 plus negative 15 would be 10. And 10 minus 4, of course, is 6. So f of negative 5 would be 6. But you guys don't have to do all of those steps. You haven't, so like written out. We can combine steps here for sure. So how do we do f of 2a? Okay, so f of 2a. Well, remember what we did here with that negative 5, right? Everywhere we saw an x, we replaced it with a negative 5. So we're going to do that same thing here, but everywhere I see an x, I'm going to replace it with a 2a. So 2a squared plus 3 times 2a minus 4. So remember, start with exponents, right? 2a squared does not mean 2a squared. That's not the same thing, okay? When we square something, we multiply it by itself. So 2a times 2a, which of course is 4a squared. And then I do the multiplication, which would be 6a. And then we would try to do any, adding, subtracting, but none of those are like terms. So we're done. That is as simple as we can make that. So then we're going to take this expression. Actually, I'm going to save C for last. It's the most complex one, so I'll save that one for last. So I'm looking at D here. So I want to find negative f of a. So what that means, essentially, we're going to take our function, we're going to plug a in everywhere we're seeing x. So a squared plus 3a minus 4. And then I'm going to take that whole thing and make it negative. Make it the opposite of what it was. So what do I need to do to simplify that, right? And so, of course, a squared is just a squared, and of course 3 times a is just 3a. So it's actually pretty simple. A squared plus 3a minus 4. And I want to take the opposite of that, right, which would be, of course, that'd just be negative a squared minus 3a plus 4. So negative f of a will be equal to that. Something you guys may not have seen before, but it's really not too bad. So it's, kind of going to just do that last, all right, since it's on the outside of the function. All right, last thing, again, something a lot of you guys coming out of Algebra 2 would not have seen before. So I want to take this function and I want to plug this into it. All right, so we can see now. We're getting just the idea that every time we see an x, this is going in there. Okay. So f of a plus h equals, so we're going to take a plus h, and we're going to square it, plus 3 times a plus h, and then we're going to like minus 4. Okay, so I replace that x with an a plus h, so it's getting squared. Replace that with x, that x with an a plus h, so it's getting 3 times that, and then the minus 4. So we need to do this. Right? So we need to go through all these steps here. So, ooh, that's fun. Try that again. So what we want to be careful here about doing is with that exponent. And again, I know something we've talked about here, but we cannot just drop it in. That's inappropriate. So what that means is to take a plus h times a plus h, which is a squared plus ah plus plus h squared, which is a squared plus 2ah plus h squared. And so, of course, 3 times ah is 3a plus 3h. So I'm just going to bring that down, plus 3a plus 3h, and then minus 4. And then we just need to look for any like terms, which I don't see any of. So we have a squared, this is not an a squared. These are just an a, so it doesn't go with that, right? And h is not an h squared, so none of these go together. So that's all we can do, actually. That would be as simple as we can make it. So it may have seemed really complex. There really wasn't much to do. F of a plus h equals that. So, but you do want to look for like terms when you're done with that, just to make sure. So those should match up pretty well.